This podcast is brought to you by the Environment Institute of the University of Adelaide. For further information, visit our website at www.adelaide.edu.au/environment.
The urban heat island has been researched. Well, the first paper that I could find on the urban heat island was in 1820, where a gentleman, Luke Howard, reported that it appeared to be hotter in London than in the surrounding areas, and began some research to try to explain why that was the case. Since then, the urban heat island has been a fascination for climatologists, and significant studies have been carried out in London, in several studies, Vancouver, in Tel Aviv, Singapore, Athens, Seoul, and even in Melbourne. And generally the research shows that the urban heat island, which the technical definition is the difference between the surrounding rural area and the city, can be seen to be due to a number of things: the difference in radiation exchange, both the solar and the long wave, difference in wind patterns, difference in the type and extent of vegetation, difference in the materials and the thermal properties and the water absorption properties of the materials, and a difference in the anthropogenic heat release between the rural areas and the city. The anthropogenic heat is the amount of heat produced by human activity. And we can see here that some research, the first one here shows a recent research in London, and this one is in Singapore. And the urban heat island kicks in between sunset and sunrise. So when people talk about the urban heat island and the hot days or something, that is not actually a typical urban heat island. The urban heat island is the difference, mainly is the difference between the city temperature and the rural temperature during the night time, not during the daytime. And you can see here that in London, between the hours of here, where it's hotter, is in the early morning hours, and here in the evening hours it starts to kick up. And in Singapore here you can see between sunset and sunrise is when the urban heat island is occurring. There's been a correlation found between urban population and urban heat island. So what would be the maximum temperature that we would expect in Adelaide, between Adelaide city and the surrounding areas? What if you're very, guess one of those? Adelaide population is about 1 million, so perhaps we would expect something like 9 degrees difference between maximum heat island effect between the rural surrounding areas and Adelaide. And it's due, as I said, for a number of reasons: the difference in the way in which radiation impacts upon the rural areas and the city areas, the difference in the way the wind is affected between the rural areas and the city areas, and the difference in the way the wind acts around buildings, and anthropogenic heat. So these are just some data. The anthropogenic heat that's been measured, very difficult thing to measure in cities, but you can see that it varies between 3-4 watts per square metre and perhaps up to 200 watts per square metre. What does that mean? Well, if you're out in the sun today, you'll probably, the radiation might have been something in excess of 1,000 watts per square metre. So the anthropogenic heat maximum is maybe a fifth of that. So another question: where would heat be ejected in cold climates in a city? The answer is through the building envelope. So the heat, the interior of the buildings is likely to be hotter than the outside, so you're getting heat going through the building envelope. But where does heat get ejected in hot climates? Anyone have any idea? If it's cooler inside than outside, there's not heat being ejected. But there is, because it goes through the air conditioning systems. So it's the air conditioning systems that are actually providing a lot of the anthropogenic heat in hot climates. So what did we do? Our particular interest in doing this research was not to study the urban heat island per se, but we are interested in the thermal simulation of the performance of buildings. And the climate data that we have available tends to be measured at locations of Bureau of Meteorology, perhaps at airports, in Adelaide, perhaps at Kent Town. We even have ways of anticipating future climates. But what was not available to us was ways of adjusting the climate data that had been measured, say, at Kent Town or at the airport, to take account of the urban situation. And this is what our interest was in. What we did, set up a monitoring network, and we had basically 3 stations in Adelaide. Our urban sites, which I'll talk more about in a moment, and 2 reference sites, one at the Bureau of Meteorology and one in the northeast parklands, out in a site that is the nursery site for the Adelaide City Council. In the city, we had measuring networks in Cheshire Street and in French Street. And these we have a whole pile of things like this, and if you examine those really closely, because this was low budget research, they're actually plastic dinner plates stuck there. And that was a result of literally hundreds of ways of trying to get some cheap solar radiation shields that we could measure the temperature and humidity in, and turned out to be plastic dinner plates from Woolworths, actually. And you can see these are set up in grid sections along French Street, which is the little street perpendicular to Cheshire Street, and they went along Cheshire Street as well. The measuring station at the nursery looked like that at one time. When we started off, it actually had grass here, but the City Council, in their wisdom, decided to pave the area, so that rather changed part of our experimental setup. But the Met Bureau was good, and they didn't pave their standard site for us. So what did we find? This is just a typical day to explain what was going on. So if we just take the nursery site here as a reference site, that's the green line coming through here, and in Cheshire Street and French Street we measured the typical urban heat island here. You can see during the morning hours it's hotter in the city, and as soon as the sun sets it's hotter in the city. But we also measured another very interesting thing, which had been hypothesised in the literature but not actually measured in great detail. And this is a cool island effect. So during the daytime, it was actually cooler in the city. And this was an effect that we found constantly, which I'll show in a minute. And there is a difference also. This is the relative humidity was difference in the city compared to the much drier in the city compared to the reference site. So if we just look at some details the monitoring actually was over about an 18-month period, and you can see if we compare the urban sites, this is the average of all the temperatures that we took to Kent Town. This is the interesting one. 8.6 was the maximum average urban heat island, very close to the 9 that we showed before. And between the nursery site and the city sites, we in fact got an average maximum greater than 9. If we look at the urban cool island effects, it's not as great as the urban heat island, but it's still significant, and between the nursery and the urban thing, a difference of -6 degrees. There is a difference between street orientations, so we're measuring in Cheshire Street and French Street, and without going into great detail, where it's positive here, Cheshire Street was hotter than French Street, so Cheshire Street's running north-south, French Street's east-west. So where the positive line here, Cheshire Street, is hotter than French Street. So there's a difference in orientation. As I said, our main interest in all of this was to try to develop a thermal model that predicted the differences. And our model is called a CAT model. And it is based on a description of the city which is we call an urban canyon. So we sort of have a street here of width W and buildings of a height H. So Veronica will be talking about the H on W ratio. The larger that number is, the higher the buildings are compared to the width, which designates a more dense city. Does the model work? Well, yes, with a great deal of accuracy, which surprised us. Well, not really. But the red one was the reference site. In that case, it's the Met Bureau data. In here is the measured temperature, and the dotted thing is what we actually predict. So we can look at here and with some confidence say that we are predicting, taking the Met Bureau data, we can predict what happens in the city. In fact, we can actually do the reverse calculation and work out what Met Bureau should be measuring if we measured something in the city. So that was pretty clever. Just to show you a few statistics, the mean monthly temperature in the Kent town was 13. What we measured was 14.6, and what we calculated was 14.6. And most of the other statistics are quite accurate as well. And just to show off a bit more, we've recently got some very accurate data from a measuring site in Sweden, in Gothenburg, and we used the CAT model to predict, and you can see the same sort of results. We're actually predicting from a Met Bureau site what was actually measured in Gothenburg. So we can use this CAT app, this CAT software, in a number of ways. We can actually use it to look at site-specific temperature data and use that in our building simulations. We can look at the evaluation of microclimate conditions at specific locations. We can evaluate proposed planning regulations, if you like, planning proposals in terms of temperature effects, and we can use it as a research tool. And what Veronica is going to now talk about is how we use the CAT model to predict the energy consumption in different planning scenarios in Adelaide.
Thanks, Terry. So what we did was we used the CAT model and we simulate this hypothetical building. The building was actually designed by our students last year when they look at green stars. So we used the building. However, we assume that the building was surrounded by other buildings, so only one side is exposed to the sun, as you may say that. So these are some of the parameters of the building. It's brick as concrete with double low E glazing. I have 15 liters per second ventilation, 15 watts per meter square internal loads, and so on, with thermostat setting between 24, 26 in the summer and 21 degrees in winter. So we test it with different canyons orientation, as if the building is in Adelaide, so facing east, west, north, south. So the canyon run either north, south, or east, west. The building is simulated by a simulation tool called EnerWin, EC, Energy Compliance. It's developed in the United States, where I was involved a while ago. Basically, we can use any other computer model to test this, and this is the one that we chose. Basically, the model predict thermal energy. Sorry, it's an energy simulation model based on the weather conditions or weather data. So what we do is, instead of using weather data from the station, we use the CAT model predicted weather data. It takes into account the building geometry, materials, and so on, envelope properties, internal loads, and operation, and HVAC operation. So it predicts hourly, monthly, annual energy consumption, as well as heating and cooling loads and other things as well. So we look at different canyon ratios. So this basically is showing, the first one is the denser configuration. So the height of the building is 14 meter and the width is 4 meter, for example. So it's, or 4.5. So that gives the ratio of 4. And then the next is the ratio of 2. So the street becomes wider, which is the width is half of the height of the building. The next one is the width is the same height of the building. It's like 14 meter wide street and wider street even. So but we don't vary the height of the building because we want to see the effect on the same building. If we vary the buildings, then it have other variations. And also we look at pretty long, sort of wide street, which is the ratio is 1/4 or 25%. So this is just giving you an idea again of what the model by CAT, as Terry already mentioned, to say there's a lot of urban heat island effect, but also cool island. So overall, you can see how it is across the year. So some of the detail here, that the narrow street tend to have higher anthropogenic heat per meter square because it's a denser street. With the same amount of traffic, of course, that becomes much warmer compared to wider street. And also there is a clear inverse correlation between canyon width and heat island intensity. So once again, in the narrow street, you get a higher urban heat island compared to the wider street. What is interesting, though, what we found, is so we take into account the urban heat island effect as well as urban cool island effect, but also the denser the buildings, the more shade it would create to each other. So there's effect also of reduction of solar heat coming to the building during the day because the building is shaded by other buildings. So the wider the building, the more heat gain you get. So this is what we got on average, that the heating, the wider the building, actually you got, the wider the canyon or the wider the street, you get less heating load, or the narrower it is, the heating load becomes higher. And simply because although you got more heat coming in, from the urban heat island, but you got less solar radiation because of the shading. On the other hand, or similarly actually, that the cooling goes down as the street gets narrower. On the other hand, it's get larger as the street get wider because you got a lot more direct gain. So what we found actually, the wider the street, the more energy would be used by this building. So we look at a different building orientation. So that was the average amongst all of these. So the first one on the left corner, top left corner, is if the building is facing north. So you can see the total effect is slightly increasing as the building gets wider. And you can see that the heating is going down as the building gets wider. And is there any pointer here? And also as the building, the canyon gets wider, the cooling is increasing. And similarly with all other orientations. So if you look at comparing it to all orientation with different width, and you can see that once again, the wider the canyon, the more energy we found. So in general, denser building configuration could in fact reduce energy use. It's probably not what we thought would happen. What also is interesting is the denser the configuration, east and west, north, south, basically perform similar. And it actually makes sense. You know, you've got not much solar coming into the building. Doesn't really matter where the orientation is. This is what we found is quite interesting. So again, probably not what you expect, that the narrower the building, so the green line is the heating and cooling load, is actually getting less. So the wider the canyon, or the wider the street, the heating and cooling actually get increased. And that's the reverse of the heat island. The wider the street, the heat island gets less, but the energy actually gets higher. I hope that all makes sense, although that probably surprising you to see that. So in summary, what we found in Adelaide, results show that the denser development produces higher urban heat island, but also higher, greater urban cool island. The net effect could potentially actually result in a reduction in total heating and cooling energy, not the other way around. So I think we really need to see the whole configuration before we claim that urban heat island could actually increase energy use. However, we don't claim that this is the only result that you would find. Further research along the lines presented here, and including the anticipated effects of climate change, could inform planning control. So we suggest that this research will be continued by analyzing the effect of different building heights in various street width. Because we have existing street, we can't narrow the street down. So what happened? What sort of building height is most efficient? Also analyze the impact of various exterior surfaces, as Graham suggested. So at the moment, what we put is just sort of typical office building. We didn't put the green wall or the green roof. What would happen? I think that's quite a challenging task that still lay ahead of us, but that's something that we would like to see further. So that's the end of our presentation. Thank you.